Alright, I'm going to give you a lesson on the fundamental theorem of algebra. Okay. Alright, in this lesson you will use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. Sounds really complicated, but it's so simple, and I've already taught it to you, so it's going to be a breeze. You're going to find all zeros of polynomial functions, including complex zeros. This is the part that's going to involve a lot of algebra from Algebra 2 with the complex numbers. If you're good at Algebra 2, then this should not be that bad either. Okay, and then finding the conjugate pairs of complex zeros. Find zeros of polynomials by factoring. Okay, factoring. We're going to do all kinds of factoring, and I'm going to kind of test your ability to factor in this section. So let's start with the fundamental theorem of algebra. This is really simple. It just states that the polynomial of nth degree, the nth degree is this degree, has precisely n zeros. So that means you're going to look for the biggest exponent on the x, and that's how many zeros there should be. That's it. So that's the n is the 5. So rational zeros plus irrational zeros plus imaginary zeros. So we're going to have to find rational zeros. These are numbers that can be written as a fraction, like 1/3, 6, -18. All those are rational because a -3 can be written as -3/1. All those are rational zeros. And irrational zeros are numbers that cannot be written as a fraction, like the square root of 2, pi, all those numbers that don't end in the decimal form, and you can't write the whole thing without writing it. So those are irrational zeros. And then imaginary zeros, those are the ones with i's in them, which comes from the square root of -1. And that was your last lesson when we talked about complex numbers. So let's talk about the type of roots, or more like the type of numbers. A 2, would you put that as a rational number, an irrational number, or an imaginary number? Well, it can be written as a fraction, so I'm going to have to put that in here. What about -9? I can write that as a fraction too, -9/1, so that also is rational. What about 1/3? Well, I can write that as a fraction because it is a fraction, so that's rational. What about 4i? Now I is that imaginary, it's not a variable, so it's an imaginary number. What about square root of 5? That's irrational. Okay. And what about 0.3 repeating? The repeating bar just means it's 3/9, which reduces to 1/3, so this is also a rational number. And the square root of -9, that's imaginary because you can't really take the square root of a negative number unless we're in the imaginary group of numbers. How about the square root of +9? That's really 3, so that's rational. What about negative square root of 2? That one's irrational. We're not taking the square root of a negative number. The negative is on the outside. Cool. So what does this all mean here? I give you a little graph here, a picture of some roots. Roots are the places where the graph intersects the x-axis, or where y is 0. So we have, these are all p over q. Okay, that's how you find the rational zeros. And -2, that's a rational zero right here. And then -4/3, that's another rational zero. So we have 2 rational zeros. And then the square root of 2, that's an irrational zero. Okay, so here you can see the rational and irrational zeros on the graph. You can't see these. All right, these are hidden somewhere else. So we only see what we can have here. All right, so imaginaries are hiding. They're hiding in here somewhere. You can't see them. Okay? Find all zeros. Write the function as a product of linear factors and list all zeros. So the linear factors are going to be what you have, like x minus something in parentheses. So here are my zeros from p over q, 8 over q. So all these are the numbers that can go into 8, divided by all the numbers that can go into 1. That's q in the front. So dividing by 1 or negative 1 doesn't change these numbers. So this is all the ones that are possible. Okay. So looking at my graph on my graphing calculator, when I put this in, I see that we have zeros at negative 2 and 1. And using Descartes' rule, this is all the possibilities. I counted the number of sign changes, positive sign changes, negative sign changes, and then I filled in this part right here. These are the possibilities. And from this table, I can see that it bounces off. So there are even number of ones. So there's going to be 2 ones, 4 ones, 6 ones, and so on. Okay, and then it goes through the negative 2, so there's an odd number of negative 2's. So there's like 1 negative 2 or 3 negative 2's or 5 negative 2's. So looking at this table, we see that there's 2 ones in the negative 2 and 2 imaginaries, because this is the 5th fundamental theorem of algebra. Says there are 5, so there has to be 2 imaginaries. But the ones I can see from the graph are 2 ones because of excuse me, bounces off the 1, and it goes through the negative 2, so that means we have 2 positives, positive, and 1 negative, and 2 imaginaries. None of the other ones work. Complex zeros always come in conjugate pairs. You have 3 minus 2i, and then the other one will be 3 plus 2i. That's how you're going to get those. So here's our next example. Find the 4th degree polynomial function with real coefficients that has negative 1, and 3i as zeros. Well, 4th degree, that means we want 4 factors. Okay, so we're going to have 4 factors, but we only listed 3 here. So we know that there's going to be one that's negative 1, another one that's negative 1, one that's going to be a positive 3i. Well, we know that imaginaries come in conjugate pairs, so the other one must be a negative 3i. Okay, and these are my factors. So it says find the polynomial function. I have the factors, now I just have to get the function. So that means I'm going to FOIL all this out. Let me clean this up a little bit here first. X minus a negative is a positive. So this would be x plus 1, and x minus a positive 3i is x minus 3i, and x minus a negative 3i is x plus 3i. I FOIL these two terms, and I get x squared plus 2x plus 1. You should get really good at this, just writing them out. You should know how these come about. When I FOIL this, I get x squared plus 9. Now I have to FOIL these two, or not FOIL, but distribute, right? Well, you can think of it as FOILing. But I'm going to multiply the x squared by all these 3 terms and get these. And then multiply the 9 by these 3 terms and get this. I wrote this so that they line up. I wanted to line up my x squareds here so that I can just add straight down. So I'm going to go 4x to the 4th, 2x to the 3rd, and then 1x squared plus 9x squared is 10x squared, and then bring these 2 terms down, and that's my final answer right there. That is the 4th degree polynomial function with these as its zeros. They only gave you one complex or imaginary. That means you know the other one's going to be a conjugate. Multiply it all out, and you're going to get the function that makes these. Let's try one more here. Find the 4th degree polynomial function with the real coefficients that has negative 2. So we're going to do the same thing. We're going to take these and make them as factors 1 is going to be the 1 minus 4i that they gave you. 1's going to be the conjugate. Okay, you need to be taking a lot of notes. This is very confusing, and if you're just sitting there watching it, you're going to come and you're going to go, I don't know what that was. Okay, rewind it if you have to. Alright, now I'm going to FOIL this, and you have to be real careful. I'm going to ignore this for a second, and we're just going to do this part right here. I'm going to distribute this negative sign. So I'm going to get x minus 1 plus 4i, right, when I distribute the negative sign, and then x minus 1 minus 4i. Now I can see that this is a difference of squares if I regroup the x minus 1. So if I regroup the x minus 1, I have this thing here plus 4i, and this thing here minus 4i. So there's my difference of squares. I have this is the first term, this is my second term. So I can square that. That's my difference of squares. Okay, that's my difference of squares. That means I have to FOIL this now and square this. So when I FOIL this out, I get x squared minus 2x plus 1. And 4 times 4 is 16, and I times I is negative 1. So now this becomes a plus 16, and I get x squared minus 2x plus 17. Now I FOIL out the x plus 2, and I get x squared plus 4x plus 4 times what I got from here from FOILing out my complex numbers, my complex zeros. Now I distribute this. I take the x squared and distribute that. Take the negative 2x and distribute that. And take my 17 and I distribute that. And I do that when I line up all my like terms, so I just have to add straight down. X to the fourth, 2x to the third, 13x squared, 60x, and 68. There's my final answer. Okay. Okay, factoring. Now we're going to take it apart by using factoring, a technique that you did a lot in algebra. So we're going to use that now. Now some people can't see this as a trinomial. If you can, great, then go with it. If you can't, then you're going to have to use a little trick. You're going to have to replace the x squared with another variable that's not squared. So now if you see that, this is your trinomial, the quadratic trinomial, when this was really a quadratic with the x, it's already squared. Now when I factor this, I put the negative 20 times the 1 in the front, put the negative 1 on the bottom. What makes negative 20 and negative 1? Well, I believe that would be a negative 5 and a positive 4. Okay, now don't forget that I substituted the x squared with an a, so now I have to put that x squared back. Okay, don't forget to put it back. So this is this factored out. Now, these are the rational factors. I can see some irrational factors in here that I need to take apart. Depends on what they ask you for. If they ask you for rational factors, you're finished. If they ask you to find all the rational and irrational factors, you have to factor that out. Well, this is a difference of squares. If I think of it as the square root of the 5 and the square root of 5, this is a difference of squares, right? Minus and a plus. So when I take that, the square root of x squared is x, and the square root of 5 is just rad 5. So that's this part. Now that's my real factors. If they ask you for all the real factors, you're going to have the rational and the irrational factors. This was just the rational. If they ask you for the reals, then you have to take this apart and give me the radicals, because these are still real. What if they ask you for all the factors with the complex ones? Well, there's the complex ones hiding in here. We have to take that apart as a difference of squares. Now we can rewrite this as a minus if we put minus negative 4. So that difference of squares will be taking the square root of this term and this term. This is where our I comes from, because that's a negative in here. So that would be the square root of x squared is x, the square root of 4 is 2, but that's a negative, so I put an I on it, and there's a negative, I can put I on that. So when you put it all back together, these are this is completely factored with all the factors, real and imaginary. We have the rational factors, the real factors, and all of the factors, no matter what they are. Okay, we have the irrationals in here and the complex ones in here. That's a lot, I know. Let's go through one more example. I just want to show you this graphic of what we did earlier in the same color scheme. The imaginaries are separated from the reals, and the reals include all the rationals and the irrationals. One more. Write the polynomial as a product of factors. So you remember that little trick that I did? If you don't need to do that, just remember that x squared is in here squared, and this is just x squared, so this is really a quadratic trinomial, and you can factor it like this. Okay, 4 times 25 is 100, 4 plus 25 is 29. You may want to pause it here and see if you can take this apart. Alright, we have our rational factors. Now we're going to find, are there any irrationals? No, I can't really factor this anymore without using imaginaries because it's a plus. This is not a difference of squares. So I'm done with all the real factors. These are all the rationals and irrationals. If I want to find the imaginaries, I have to take this apart, right? And then that will be x minus 5i, x plus 5i, that's what this is, and x minus 2i and x plus 2i, that's what that is. And that's all our reals and imaginaries, and there were no reals, all imaginary roots in here. If you put a 0 in here, you can get the x-intercept of 0, 100, and y-intercept of 100, and it opens up. That's a good reason why you're not going to have any real roots, because if you think about a w that has a y-intercept at 100, it probably is not going to dip low enough to get down into the x-axis, if that makes sense. Okay, you don't need to know this. This is just little side notes that just by looking at this, I go, wow, I'm way up here on the y-axis at 100, and it opens up like a W. Probably a good chance that I'm not going to find any real roots. They're all going to be imaginary. Last example here, factoring this. This is a difference of squares with x squared as my first term, and the square root of 625. I hope you know what the square root of 625 is. If not, you might have to play around with your calculator a little bit. That would be 25. Now look, we have a minus here. That means there are some real roots here. This is a plus. That's imaginary roots. Okay, but since oh yeah, I know what this is. I hope you do too. Okay, so that's x minus 5 and x plus 5. So there's my two real zeros, and then something in here that I can't take apart yet. So that's my rational zeros. And there are no irrationals because I can't take the square root of this. So I'm going to have to come and square root the negative 25 and make 5i and negative 5i and positive 5i. And that's going to give me my all the factors. The real ones, these are the rationals, there are no irrationals, and these are my two complex ones. Okay, don't forget to do the Google form.